4.2.4 The Fallacy of Conventional Statistics. Much of the machinery used to explain physics and chemistry depends on the first type of uncertainty. As a consequence, a lot of the statistical tools also assume that any uncertainty is of the first or at best the second type. In the human world, it can be quite a challenge to find any examples of uncertainty of the first type. Is it possible to determine which type of uncertainty has generated some observed data? For example, consider a cow studying the patterns in the flow of food during its lifetime spent on a farm. If modeled conventionally, this is a very stable system up to the point when the cow is slaughtered for meat. Any uncertainty in the flow of food in a farm comes from uncertainty of the third type, not the first type. Take the example of business sales prediction. Most existing forecasting software assume that the underlying uncertainty comes from the mindless random sources residing in the whims of customers rather than from other competing firms. However, both the behavior of customers and the behavior of competitors are driven by uncertainties of the third type. Due to the nature of competitive markets and institutions, assuming uncertainty of the first type works a lot of the time. However, it also tends to fail most spectacularly. The attempt to model commodity market prices in the early 70s led Benoit Mandelbrot to discover that conventional statistics does not work and to lay the foundation for the study of chaos theory. Yet, we still continue to use conventional statistical analysis to try to analyze events around us, particularly in business. Conventional statistics forms the basic machinery of a lot of the analysis of competitor sales, prediction of the movement of stock markets, assessing the risk of flooding and fires for housing insurance, and so on. Yet, these are examples of uncertainties of the second and third kind, making conventional statistics the incorrect analysis tool. What makes the process of studying these uncertainties very deceptive is that under many normal conditions, they all look quite similar to each other. Thus, we may be lulled from a few decades of weather data into thinking that there are things called 100-year storms, which can be expected to happen only once every 100 years. However, competing humans and nations are very much a part of the system, and we have modified the very system that we assume is independent of us when analyzing events. Try to use statistical analysis to answer this question. Which piece should a player use in the 15th move to maximize the chance of winning a game of chess? Current forecasting approaches to answering this question may look at a few thousand games where the opponent's skill level matches the skill level of the opponent we are playing against. Using this data, we would then correlate the chances of winning for each of the different observed 15th moves. We are reasonably certain that this approach will not win any competitive games.